us made it to the CFA today. I wonder whether the people that just came back from the South Pole, John and Arian, whether when they opened the door this morning, they felt deja vu. But I guess there are no trees in the South Pole, so that's a big difference. We just had an excellent colloquium by Eric Keto, our own. Where is Eric? Over there. And we will hear more from him in a few minutes. Our first speaker is Jill Naiman from the ITC, and she will talk about neutron star mergers and our processed elements such as gold or uranium in the IllustrisTNG simulation. Then we'll hear from Joaquin Vieira, who is the colloquium speaker today. He's sitting at the end over there, I believe. Right? Yeah? From the University of Illinois. And he will talk about the spectroscopic terahertz airborne receiver for far infrared exploration, abbreviated as StarFire, a next generation experiment for galaxy evolution studies. Then we'll hear from Eric, who will talk about the formation of low mass stars, CO, desorption rates, and molecular mass of the galaxy. And finally, we'll hear from Sagi, who will tell us about the beautiful instrument that he developed, FIOS, which is the Fabry Perot based extreme high resolution instrument. Cheers.
All right. So congratulations to all of you for making it out through the tundra. I appreciate it. I'm sure it had everything to do with science and nothing to do with free food. So I'm going to talk to you today a little bit about what we've learned by tracking the neutron star merger products in the IllustrisTNG simulations. If you're kind of over neutron star mergers at this point, I'll point out that there are a lot of different kinds of science that are being done with the IllustrisTNG simulations. Listed here are just a few people that are involved, and so if you don't want to listen to this talk, just know that you can learn about galaxy physics and large-scale structure through these people as well. And so I feel like no talk this point going forward about neutron star mergers is complete without devoting an entire slide to showing this fantastic LIGO detection. And if you can't read it again and you've forgotten for some reason, time is on the bottom and frequency is on the y-axis here. So here is that slide. But of course, the coolest part of this discovery wasn't just the gravitational wave signature, which itself is pretty cool, but also the fact that it coincided with detection of gamma ray bursts in a variety of instruments, and then also in the X-ray, UV, optical, and eventually IR. So this was very exciting. And so we've learned two things from this particular detection. One, that neutron star, or neutron star black hole mergers do exist, so that's very exciting. And also that the R process likely powers the emission. And so we know the second thing by all of the high cadence and also multi-band detections in many, many different wavelengths. And so from all of these different wavelengths across many different instruments, we can concoct a observationally derived bolometric luminosity. And so that's what's plotted in the gray points here. And we can compare this luminosity to curves derived from theoretical R process radioactive decay. And so here are shown two different lines. So the orange is assuming 0.05 masses of R process material was produced in this merger, and the blue is 0.01. And we can see that the observational points fall in between the two. And I will point out that there are a possible other few explanations, like nickel decay, that I'm not going to talk about, but it's most likely that our process is powering this emission, and I'll refer you to Maria Drout's paper for more information. So I've been mentioning the R process, and maybe you need a jog in your memory about what that is. Basically, the R in R process just stands for rapid capture of neutrons over a time scale that is short with respect to beta decay. And so I'm going to focus on europium in this talk, and this is one such R process element. So the R process requires environments that are, of course, neutron rich and also dense, so something explosive like a supernova type 2 or a neutron star merger. And the R process from neutron star mergers has been something that has been modeled for quite some time before we ever had a direct observation. And so here, this is from quite some time ago. If you can't see it, this is around a few decades. But right, so this is showing the high densities that develop in these neutron star mergers over very short timescales. If you can't read the time tick at the top there, it's in milliseconds, so this is a few milliseconds of time. And you should also note that there are these tails that are produced that are very high density and also are going to be enriched heavily in our process material at the end of the simulation, and those things are incorporated into the gas surrounding these objects. And so this relates to another way that people have been indirectly observing the results of neutron star mergers before the direct detection that we had last year. So before directed observations of neutron star mergers, folks relied on inferences from things like the abundance spreads of our process elements like europium in the Milky Way. So here is one such collection of observations of stars in the Milky Way. And if you're not used to looking at these things, or again, you're just waking up, we all got to sleep in. So here's a little reminder. So things that are old are going to be low in Fe on H. Things that are younger are going to be high in Fe on H. And then on the y-axis is telling you something about the pollution track. So in this case, if you're lower in EU on Fe, you're polluted more by supernova type 2. If you're higher on EU Fe, you have something more like either a special kind of supernova type 2 or more likely a neutron star merger. So we can compare this to something less exotic, so like Mg on Fe distributions of Milky Way stars. And so again, this is telling you about the relative contribution of pollution from different kinds of supernova. And so what I want you to take away from this is that these things are plotted on the same y-axis and x-axis, but that you should focus on the fact that the spread in EU on Fe is much larger than the spread in Mg on Fe at low metallicities. And so that's telling you something about how EU is produced, specifically that it's something that happens infrequently at early times, so that some stars get a lot of our process enrichment, some don't. And also it's telling you that in the gas phase, this stuff isn't heavily mixed, so that stars that form from these enriched gas phases retain those levels of enrichment. So the basic idea is that while something frequent and ubiquitous like supernova type 2 are responsible for magnesium, something less frequent like neutron star mergers have to be responsible for europium. Of note, there's some theories that say that there could be these special types of supernova type 2 that maybe produce our process. I think, from what I've gathered anyway, as it might be controversial, but neutron star mergers are the favored production mechanism for our process. So this is sort of a summary of how people sort of inferred the existence of neutron star mergers before we had a direct observation. So with a cosmological simulation like IllustrisTNG, we have many Milky Way-sized halos. And so from things like this, we can ask ourselves two questions. So one, can we model a distribution of our process elements, those dispersions at low metallicities that we observe in the Milky Way? And because we have not one but many Milky Ways in our simulations, are there specific properties of the individual galaxies that determine the shape of its EU on Fe spread at low metallicities? So we attempted to answer these questions in IllustrisTNG by adding a prescription for neutron star mergers and then looking at the europium produced in events and how it's distributed in halos with masses and properties that are similar to the Milky Way. So this is the necessary pretty picture of galaxies that you can produce in cosmological simulations. So this is very important that one shows this if you're talking about cosmological simulations. Okay, moving on. Right, so the detailed modeling of neutron star mergers and the subsequent R process ejecta is very complicated, to say the least. You have to follow the detailed evolution of compact binaries and common envelope evolution, the details of nucleosynthesis in these very dense neutron-rich environments. Luckily for us, though, the overall distribution can be relatively simply modeled from a single stellar population as a delay time distribution. So it has a relatively simple form. So this delay time distribution basically accounts for all of that complicated binary evolution by having a delay between star formation and when we expect neutron star mergers to start occurring. And then the rate drops off as 1 over t. Yeah. Oh, yes, and also we're just assuming here that there is about 0.05 solar masses of our process material produced in each merger, and that the very small fraction of that is europium. Okay, so now some actual results. So here is the simulated compared to observational EU on FE versus metallicity for all of the stars and all of the Milky Ways in the IllustrisTNG simulations. So the blue histogram is the mass-weighted histogram, again, of all stars and all Milky Ways in the IllustrisTNG simulation. The white lines are confidence intervals, just to sort of guide the eye for the simulations. Red is for observations, with the dashed lines for each of those things, or the medians for each of those things. And then there's individual observations I've highlighted with points, both from the thin and thick disk and also from the halo. So one thing you can see is that we reproduce the spread at low metallicities fairly well. Also, there's a difference in the relative locations of these things. So things that are lower metallicity, higher, tend to have higher EU on FE spreads. Those things occur in the halo, while things that are more high on FE on H and less enhanced with europium tend to be in the disk. And so I will refer you to the paper for the actual discussion of this, but we tend to reproduce this overall trend as well. So since we're short on time, I'll just go right into where does this come from. So if we look on the left, I think your left, you can see the europium distribution as a function of time. So time, europium distribution on Y. And of note, you can see that highly europium-enhanced things tend to form early on. And so this kind of makes sense if we look at the cosmological gas phase europium distribution as a function of time. And what you can see basically is that it becomes more peaked as we go from high redshift to low redshift, meaning things become more homogeneous. So there just isn't a lot of gas that is highly or less highly enhanced in europium as time progresses. So we have to form things that are very enhanced in europium at early times. Okay, I'm almost done. Also, I'll just breeze through this, but we also found the strongest correlation between high europium enhancements and galaxy properties has to do with the amounts of early star formation, with more star formation being correlated with less europium enhancements. And so just to guide your eye, basically these trends kind of go like this. So while there's no trend at present time, at early times, if you have a lot of star formation, you're going to have more mixing, and then you're going to have less europium, essentially, less europium spread. Also, just to guide your eye, this is where Mg on Fe in the gas phase lies. So there's not a lot of trends, and there's not a lot of change with time. And we also checked a bunch of other stuff. Again, look at the paper. Don't have time to go into it. This was the strongest correlation. So since I'm running out of time, I'll just put these up and say the most important takeaway from this is not just that we can do cool things with tracking neutron star mergers, but also we have this opportunity in cosmological simulations of high resolution that we can tie galaxy evolution and chemical evolution together. So thank you. That's a nice philosophical idea. Yeah, so if you want to look for happy civilizations, maybe you can look for galaxies that didn't have a lot of, or had more star formation at early times.
And by the way, it's also sensitive, of course, to the IMF. If the population 3 stars are so heavy, then you would have, I guess you didn't put that much together.
Yeah, so we used a relative, I mean, since, we're really, to do these high resolution simulations, they take, months of time, so we only had time to test one prescription. But the Riga simulations that are being performed with people at HITS, they're actually looking at a bunch of these different things. So assuming different distribution, like delay time distributions, IMF, input parameters, those kind of things, to look at more sensitively and at higher resolution what happens to your europium in our process.
Yeah, so I'm a big fan of our process coming from neutron star binary.
All right.
My question is a bit more about the details, which I think are important here and tie back to what you're saying. So what did you assume about the locations of these neutron star binary mergers relative to the galaxies and the overall mixing of the material into the galaxies? Because I think that could really affect
Yeah. So we ignored a lot of fancy stuff. So for example, we ignored any kicks, any birth kicks. So they're basically just distributed sort of stochastically depending on stellar density. So we didn't do anything fancy that way. We did look a little bit into different mixing prescriptions. So the resolution of our simulations is relatively high. It's 10 to the 6 compared to actually resolving a neutron star merger product. So we did look into if you assume that is distributed over smaller or larger masses, how does that affect things? Overall, basically it affected more kind of the shape of that EU on FE and the overall normalization, but the relationship between the high FE on H and the low FE on H, that spread was still really relatively robust. So I think that's heartening. But yeah, there are some caveats involved.
Oh yeah, so I was just wondering, how do you determine what fraction of your stars in a galaxy becomes like a binary star?
Yeah, we basically just use, we use kind of the delay time distribution as basically a probability that in a certain population you're going to have a neutron star merger. So it's, we're not assuming a continuous function. We say, okay, I have the birth of stars. I have some probability that a neutron star merger is going to go off. So yeah, so that's what we did.
Any other questions? Go ahead, James, and then after that.
So is europium the only tracer that you can use for this? Are there others? Because the different tracers might be in different peaks of the art process, and the different peaks might come from different channels.
Yeah, so for this we just use basically, so the tag we actually used was like, this is the amount of our process material that's ejected. So you could definitely follow something else. I assume it would just basically scale, so we didn't have any kind of fancy different channels. Like the Auriga simulations are looking at, for example, if you have some stochastic process in supernova type 2 versus neutron star mergers, what your difference in our process might be. So they have a little bit of that, but we just did something pretty simple.
Correct me if I'm wrong, but is this tracer europium traced in an optical line that is seen in these stars?
Yes, I think so. Is it optical or is it, I don't remember. Is it optical? It's optical, that's right, yeah.
So my question is, are you aware of any analogous infrared transitions? There's certainly iron lines in the infrared, and the reason being that you can trace these stars to much higher extinction in the plane if there are infrared counterparts.
Yeah, that's interesting. I'm not sure, but that's something to look into. I can't recall. But yeah, that's interesting. Mm-hmm.
I decided to change my talk this morning because I thought it'd be more fun to tell you about something, an actual recent result, rather than some result we may have in 7 years. So I'm going to talk about water as a way to measure the star formation rate of galaxies in the early universe. And the punchline is basically here. These are high redshift galaxies ranging from redshift 2.7 to 3.5. These are the images are about half arc second resolution. And these are with ALMA. These are about 40 minutes each integration. And these are images of galaxies that are strongly lensed, so that's why you have the ring-like structure, in water. So this is the moment zero image in water, right? We're seeing galaxies cross the universe, cross cosmic time in water. So I think this is a neat demonstration of the power of ALMA. So why would we care about water? The short answer is that water, well, it's an abundant molecule. You know, the most abundant molecules, there's H2, there's CO, and then water is kind of the third. Studies in the local universe are very difficult, obviously, because we can't look through our atmosphere. But in the last sort of decade, there have been some interesting measurements done with Herschel. Before that was ISO, but really limited, but lately with Herschel, that showed that water is a really good indicator of the infrared radiation field, so the total infrared luminosity, which is the best tracer we have of star formation rate. Okay, the observation, the empirical observation, was just that we saw the ratio of the luminosity of water to the total luminosity was constant over multiple decades of luminosity. So why is this? You can think of water as tracing kind of the kinetic energy of the molecular clouds. And so it's thus highly complementary to studies of CO, which you can think of as telling you the star formation potential. CO is tracing the H2. And water couples efficiently to the infrared radiation field, but not to wavelengths shorter than 50 microns. So the cool thing is that it's sensitive to the total luminosity from star formation, not from the AGN. Okay, so that's why we think it's one of the best star formation tracers. Empirically it is. Understanding exactly why is, I think, a little bit unknown. This is a plot of the luminosity coming out in a line over the total luminosity. And by this, I mean, the total luminosity across the whole galaxy versus one line. Okay, and here's what's usually the brightest line is ionized carbon, C+, which is at 168 microns. Okay, and this is the brightest line in the galaxy. And you see that it traces star formation, but it's not so well correlated, particularly because, well, exactly why there's this downward trend is still open to debate. Currently, the thinking is that it becomes optically thick when you get really intense star formation because you get really dense clouds. Here is one of the other common molecular tracers, CO. And again, you see that it's really tracing the star formation potential, not necessarily the star formation rate, because it's really tracing, this is the second most abundant molecule in galaxies, so that's tracing the fuel for new stars. And it's not well correlated. This is water. So you see water brighter than CO, not as bright as C+, but it's flat across 4 or 5 orders of magnitude in luminosity. So it was making this plot that kind of gave me the idea to do this with ALMA and do this with resolved in galaxies. So we want to pick apart an individual galaxy and look at this relation holds across different scales of star formation. And why we would want to do that is that for measuring the total star formation rate, usually we do this with the total infrared luminosity, which means getting multiple bands in the continuum, particularly kind of above the on the Wien side of the black body, which is really short wavelength for ALMA and difficult and expensive. Okay, so you have to have kind of multiple continuum bands, or we thought we can just get one long wavelength band and we're done. So for the future, this is what we wanted to calibrate. So here is a plot showing the water luminosity from water versus infrared, and again you see that nice correlation. These are low redshift galaxies, infrared galaxies. These are high redshift ULIRGs that have been measured. And this is like every line water, or all the galaxies that have been detected. So it hasn't been very well studied. And then these are the 4 galaxies that we'd study with the South Pole Telescope sample, which I'm going to talk about in the colloquium. So here's the data. So 3 images of the galaxies we chose. And again, this is, an interferometer is an IFU. You can think of it like that. So for this image, we have a continuum image. This is not the continuum. This is the water line that we've integrated. So this one has low signal noise. These two have a higher star formation rate, so the lines are brighter. And weirdly, ALMA messed up. Denis can tell me maybe how. But they observed it twice accidentally. So it had double the integration, and they were brighter. So these ones look really nice, and that one was kind of ratty signal noise. These are the integrated line spectra. So these are very well detected in water. So this is now looking at water resolve. So this is on resolve scale. So this image right here, there's the beam for scale. It's roughly half arc second resolution spatially. The grayscale image is the continuum image from the data cube. And the blue contours are the water. Okay. Here is every pixel now. So we take every pixel value. We're not technically measuring infrared luminosity. We're just taking the continuum value and then dividing by the total luminosity that we'd measure from single dish measurements. And these are all the individual pixels that we're measuring. So we're measuring this galaxy on roughly kiloparsec scales, okay, and water. And so, our assumption was right. These are largely flat versus redshift. Here in that dotted line, this is that trend that I was showing you there to our fit. So there is some variation across galaxies, and there's some spread. We have 2 more things that we need to do to, before we finish this work. And that is that we need to do a pixelated lens modeling. So right now we're just working in the image plane, but what we really need to do is work in the source plane. So we need to get a lens model from the water itself. And that takes 3 months. And then the other thing that's approved, and it's just in the queue with ALMA, is band 9 or 450 micron continuum imaging. So once we get that, we can actually directly measure either the dust temperature per spatial pixel or the total luminosity. Luminosity goes as temperature to the 4th, right? So that we hopefully, well, it might. I guess I shouldn't have an opinion on which way it goes, but I'm assuming that it's going to make this correlation tighten up a little bit once we do these 2 things. So to me, there's just a really cool gee whiz factor of we're imaging these galaxies in water, and it's a really powerful probe for the star formation rate indicator, and it's optically thin. And for ALMA, this is fairly trivial. So I think this is going to be, in a few years, this is going to be very routine and a powerful observable for ALMA in the high redshift universe. How this works exactly, so here's a typical infrared luminosity. So like I was saying, if you want to measure the total infrared luminosity, it means, this peak moves with temperature. The total luminosity is going as T to the 4th. You typically have to measure a few photometry points to constrain the peak and the dust temperature. That gets really expensive with ALMA up here. This water line for us is here at about 980 gigahertz, so that's what we're measuring. We're in this transition right here, which is rotational vibration, so it's being pumped by 100 microns, and we're seeing this 988 gigahertz line. The AGN is affecting these higher order transitions. So if you want, the water can be an AGN indicator, and traditionally that's what people try to use it for. But we're focusing on kind of the fact that it can be insensitive to AGN and just show us the star formation rate. So that was it.
Water also appears in masers in our galaxy around young stars.
Mm-hmm.
Is the contribution from masers negligible to the total water emission?
That's a good question. I assume it's negligible, but we'd need to ask Gary, do you know that?
I suspect that it's negligible.
Yeah.
The filling factor is quite
Yeah.
small, but I don't know in these particular cases.
I mean, this would be coming from, on these scales, massive molecular clouds, right? From the whole galaxy, so.
That would be one way of explaining the correlation, but another one would be that the dust is the agent for making the water.
Oh, yeah. So the dust is probably a catalyst.
Yes.
Yeah.
Well, just to pick up on that, we know from SWAS, from Herschel, that the gas phase water that we detect is a surface phenomenon. That within these clouds, it quickly freezes out as ice, and 99% of the water is in ice and not in the gas phase. So what you're detecting are the surfaces of clouds, and that would be sensitive to the UV. And so I'm wondering if the correlation that you're measuring is analogous to the C+, in the sense that both are sensitive to the UV field, which of course is generated by star formation.
Yeah.
So
Well, but that's just because the C+ has become, well, we think it's because it becomes optically thick, and so maybe the water just doesn't. So.
Well, the water is optically thick, but effectively thin.
Yeah.
The tau is
Yeah.
tens or higher, but those photons get out of the cloud, so it's termed to be effectively thin. But what you may be seeing here is simply something analogous to the C+,
Yeah.
but without the optical depth complications of the C+.
Yep.
James?
So is the ratio of states in the water atom affected by the CMB at redshift of 3-ish? Is that 10 Kelvin roughly at that time?
Yeah, but it's shielded, right? So I think, I haven't calculated it, but I think it should be fine.
The density is much smaller, but the CMB is much smaller than the massive stars in the sea.
Yeah.
But of course,
And at these frequencies, these are pretty high frequencies for the CMB. So it's more of effect usually on CO at low J.
You're not going to pump this with CMB at those redshifts.
Yeah.
So are you going to need lens galaxies to use this separation for 3, or is that just going to be a specialization?
Well, so if you're resolving these, the lensing doesn't matter because lensing preserves surface brightness, so they'll be equally bright. For us, that's gaining a spatial resolution effectively. So for single dish observation, the lensing helps a lot because it's the total brightness or the total flux is going up as the magnification. So it's typically about 10. So that saves you about a factor of 100 in telescope time. But because we're resolving that, we lose that effect, but we gain, effectively, we're stretching the galaxy larger by the square root of magnification, so about 3. So for us, it's gaining us here. The lensing is benefiting us here for this particular measurement. The first measurements that we did with Herschel of lens systems, there it was unresolved, so there we were gaining just in total integration time. That depends on what you're trying to do.
One comment to make is that most of the mass in water is in the gas phase in galaxies, but the little bit that is in ices is most important for that.
Yeah.
It's very different phases.
Yeah.
And this water that you detect is not necessarily an indication for life in the sky. It's not ice.
Well, it may show that there's swimming pools at redshift 3, though.
In our galaxy, a typical dense molecular cloud, 99% of the water is in the form of ice and not in the gas phase.
But isn't on these scales, that would just be the inner core of these clouds, right? Or
No, within about 5 AV, you've got of the surface.
yeah, okay,
You have conversion almost entirely to ice.
yeah.
In terms of the mass of water in the galaxy, what carries mass?
I don't know that I would answer off the top of my head. I mean, it would have to be in translucent clouds, because if you have gas that has an AV of less than 4 or 5, water always wants to freeze out on cold grains, but in low AV regions, UV photons photodesorb them and keep them off of the grains. But once you get a region with an AV greater than 5, like a dense molecular cloud, there aren't enough UV photons to kick the water off the grains, and it just accumulates as a huge reservoir. So if you have a lot of molecular gas and molecular clouds, almost all of the water will be in ice.
So the measured integrated values for these galaxies, across the whole galaxy, the AV is about 4. And then, of course, if we start resolving, it's going to be very.
That's where the story is going.
Yeah.
Very interesting. Let's thank Joaquin again.
Okay, so we're going to go a long way in different spatial scales in this talk. Now, to begin with, we start with the formation of low-mass cores, or specifically the starless cores. And these are small clouds of molecular gas that are found in low-mass star-forming regions, and they're quite common. They're 1 to 10 solar masses, and they have 2 defining properties. One is that they're in hydrostatic, quasi-hydrostatic equilibrium. So this is a picture of the column density as AV on the vertical axis versus R. and the observations are in red, and the hydrostatic density profile is in black. And you see there's a very nice fit until you get to the edge where there's some fluffy material. And the second feature is that they have these kind of sonic line widths. So again, this is a C18O and a different core, L1544, compared with a simulation of just a static core, showing that the line width is just slightly broader than thermal. Now, what makes these useful for, particularly for people doing research in the ITC, is that if you can define the density of the core to say I have confidence in the density, then I can calculate the temperature, and the temperature is the this red dashed line here. Okay, so the temperature is in radiative equilibrium with external starlight. So that's very easy to calculate. So I've got that temperature, and then there's these things are often slightly contracting. There's just on the hydrostatic profile, there's a small sort of alpha parameter contraction, right? So that's this black profile, a subsonic contraction. And given the density structure, I can say, okay, now I can start working on my models of chemistry and abundances. And so I've got here, I've plotted the abundance of H2O, C18O, and N2H+. Now, these molecular abundances are necessary as tracers of mass in the galaxy. So just as a reminder, we think that the mass in our galaxy in molecular hydrogen is like 10 to the 9 solar masses, and H1, 5 times 10 to the 9. And there have been a couple of papers in the literature, one by Rowan Smith here, and she suggests that based on numerical hydrodynamic simulations coupled with chemistry, that half of the molecular mass in the galaxy is not seen in either CO or H1. So that means that's molecular hydrogen gas with CO or H2 abundance is too low to be detected, and possibly higher fractions in external galaxies. So that means that number of molecular hydrogen ought to be 2, according to their simulations. And secondly, there's some papers saying that C1, atomic carbon, is a more reliable tracer of mass than CO. And as Stella Offner noted in her paper, it seems a bit odd because atomic carbon is, after all, an atomic line, and CO is a molecular line. So what we found in our study of L1544 was that there was a discrepancy in the CO abundances between the theory and the observation. So all right, so what we're deriving, so this is AV here versus the log of the abundance. So we're deriving a CO abundance necessary to match the observations that look like this. And some of these chemical codes are showing up with the CO confined in this boundary layer. Okay, and the difference between the two is that in these kind of codes with the standard rates, there's the CO here is all going into ice. Okay, and we suggest that rate is the desorption rate for CO off of the ice is 30 times too slow. Okay, now, okay, so how did we come to that point? So we said, well, we take L1544 and we have observations of C18O and C17O, and these molecules are emitted in the boundary of the core. So this is the core in log radius and density and velocity here at radius. So the CO comes from out here where the velocity is basically 0, and so that gives us estimates for the exterior, the envelope of the core. This N2H+ line is a very high density tracer, so that's telling us something about the center. And it's a little bit hard to see, but the splitting on this line here is what gives us this velocity. So we say, okay, so our guess is that we need this velocity profile and that density profile. And this succession of profiles comes from just a numerical calculation of the collapse of a hydrostatic sphere. You just barely remove some of the energy and it begins to collapse this way. And we have a very simple model for carbon chemistry, which is really pretty much just the grain surface reactions. So we've got ice, CO, carbon and C+. And the ice, the CO gas is desorbed from the ice by cosmic rays, and it's this rate that we have a problem with. Okay, now there's not a whole lot else going on here, so we're able to narrow it down that way. And if we turn that rate up, then we can get the abundance of CO here, which are these colored lines. This is the density of the core versus radius. So we turn that rate up and we get the CO abundance in the gas phase going up. So we say, well, what is the reliability of this model-dependent derivation of the rate? Because after all, we've got a structural dynamical model for the density and temperature, chemical model for CO, which is based on assumption of grain surface chemistry, not to mention rate of transfer. So this comes from some other studies. So we did get a Herschel observation of detection of water in this cold gas with the Herschel wideband spectrometer. That's this line here. And we modeled this the same way as we did with the carbon chemistry. So it's just grain surface reactions. And in this case, the water is desorbed by ultraviolet, and it freezes back onto the grains. And from that observation of the wideband spectrometer, we came up with this model for the high-resolution spectrometer. So so we said, well, the water abundance ought to be something like this with radius and give or take some uncertainty here. Then we would get a prediction of an emission line here, an absorption line here, and this is the wideband spectrometer. It doesn't look like a good fit at all. But the argument was that this was foreground emission. And kind of the interesting thing about this is that Paola Caselli, who's now a director at MPE, said she looked at this model that we had made and she threw out the entire GTO program and put all 18 hours of observations into this core to track down this line. And we saying, wow, that, and you know, she was right. And so here's the wideband spectrometer, and then the red and the black are just two different epochs observing, but here's that spectral line in emission, absorption, and here's this foreground CO, which doesn't have anything to do with the core that we're studying. So our water model works great. So this is our model for the H2O gas, and as Gary was saying, it's all frozen out here at high AV. And the dotted lines are, in fact, this Hollenbach, Kaufman, Berg, and Melnick model. And so the fact that the complex model, which has 1,000 reactions or something, matches the simple one means that the complex one might be right. And furthermore, we had yet another observation, and this is this ortho NH3 line at 572 gigahertz, also coming from Herschel. So we take the same dynamical model, and we put it in the rate of transfer code, and it comes up with an excellent match to the observation. So again, it's kind of a prediction as opposed to a postdiction, right? So then we said, all right, so we're fairly confident on the dynamical model for the core, and we know that our model for gas phase, grain surface chemistry is working, at least for the water. It doesn't mean it's working for the CO necessarily, but it's a good indication that those are the important reactions. Okay, now why would the CO desorption rate, why would the standard rate not be reliable? Okay, so now these rates are calculated in this way according to Hasegawa and Herbst and Leger, right? So you say there's the evaporation rate per molecule is given by this characteristic frequency and the exponential, and this is the binding energy of the molecule on the grain, and the desorption temperature. Okay. Now the cosmic ray desorption rate, then they say, is given by the amount of time that the grain spends above the desorption temperature and this evaporation rate. And this factor F is in the half-life here, and this is the time between cosmic ray strikes. And this picture just shows what happens is that as you turn this is they call temperature program desorption. So you put your frozen CO in an experiment, and you turn the temperature up slowly over time, and you hit 26 degrees, and it all just comes streaming off, right? So this is that temperature. Okay, now there are many uncertainties here, and one is the desorption temperature. Desorption energy depends on the chemical composition of the ice. So we know what it is if you have CO ice, if it's bare grain, if it's water ice, but you mix all these things up, and it's not so clear. And the ice could be amorphous or crystalline, and there could be other properties, other desorption processes, H2 formation, and so on. Okay, so that's so we suggest that if you turn that rate up, that will improve this model, and you'll get a match to the observed data. All right, so it's the simplicity of the starless cores that gives us this opportunity to study these processes with a well-defined model. So then we can get at some of these in detail, grain surface chemistry and gas phase abundances, and these will inform the numerical simulations, which are depending upon these abundances to fairly high level of certainty, like a factor of 2, right? They're saying they're making predictions on a factor of 2. So anyway, that's the talk.
I'm just curious, with the cosmic ray ionization rate has to be ridiculously high to explain what you're seeing relative to the change in...
No, we're using generally like 3 times 10 to the minus 17. So we're only considering, when we were doing this study, we considered rates from 1 times 10 to the minus 17 to 1 times 10 to the minus 16, and the one in the middle, seems to be fine. So it's not right. So Thomas Biswas was here last week, and he was talking about very high, CO and C1 in environments with very high cosmic rays, and that's different. Yeah, so.
What's the typical energy range of these cosmic rays?
Sorry, what?
What are the typical energies of these cosmic rays?
Energies of
The individual cosmic rays. What energy range? 100 GeV, the energy of the cosmic rays.
These are generally considered to be the iron cosmic rays, the ones that penetrate the molecular clouds. So they're, I forgot what the GeV is, but that's what they're, yeah.
And the low energy ones are more common. So most of them are 100. Let's thank Eric again.
Okay, can you hear me? Not really, right? Okay. So I'm going to present a project we are working here at the CFA and at the CDP, which we call FIOS. It's a Fabry instrument for oxygen searches, even though the goal of this talk is actually to get some input from you for other science cases that you think that this kind of instrument will be beneficial for. I'm not in charge of the acronym, by the way. Let's take no responsibility whatsoever. So the goal, we started this project because we have a goal of detection biomarkers in exoplanet atmospheres using transmission spectroscopy. This is one of the holy grails of exoplanet studies. And the idea there is that if there is an exoplanet that transits the star, light from the star goes through the atmosphere and there will be some absorption. Now, if the star has oxygen, molecular oxygen in its atmosphere, then it probably have the same absorption comb as the one that is found in our own telluric lines that we try to avoid all the time. So those two combined with the exoplanet atmosphere is actually creating an absorption cone. Now, if the exoplanet is actually have some barycentric movement in the line of sight, then the transition cone of the exoplanet atmosphere will be shifted a little bit with respect to the telluric lines, and then we will be able to measure it. One of the things that we noticed when we started is that actually the lines from the exoplanet are much narrower than the lines from the telluric, and the main reason for that is actually line of sight refraction. It took me some time to understand what is the source of this effect. So those lines that we actually, the absorption lines in the exoplanet atmosphere are much, much narrower than the one that are found in our own atmosphere, the observed one. And then it came to me, it came to us, we are working as a team, that we actually need to increase the resolution in order to really be able to measure that. We would like an optimal resolution would be somewhere between 3 and 5 times 10 to the 5, which is roughly a quarter scale of 3 to 5 times the maximum efficiency that we have, the maximum resolution that we have from modern shell spectrograph. For example, GCLEF has a resolution of 10 to the 5. But there is a problem with modern high-resolution spectrograph, the way that we work, in achieving much higher resolution for larger telescopes. And this is actually implemented in this resolution equation, in which you can see that, okay, the resolution is proportional to the size of the beam inside the instrument over the size of the telescope diameter. I have a bigger telescope diameter, I need a bigger beam, and it comes up to ridiculous size that the instrument is the size of the telescope, and that makes everything impossible, basically. So there are all kinds of ways that are trying to solve this problem. Pupil slicing in one of them. At higher wavelengths, you can actually use AO to improve your sync, size the sync function, and then you get higher resolution. But at around 750 nanometers, AO doesn't work that well. Pupil slicing have its limitations, and therefore the way that I thought of solving that is actually to use a totally different disperser than the regular shell grating that we use in modern spectrographs. And what I thought of using is a Fabry-Perot interferometer, or an ettalon. And that's basically a piece of glass that has 2 reflective surfaces on each side, partly reflective surfaces. And as a wave will pass through this piece of glass, every time that it's doing a pass, it will gather the phase phi that you can see above. Now, it's kind of straightforward to add all the electric field on one side, on the transmitted and the reflective side, and then to find the transmission intensity and reflective intensity of this piece of glass, this ettalon. And you can see that because the transmission and reflection are a function of the phase, and the phase is a function of the wavelengths, then therefore we can actually achieve very, very high resolution. F, by the way, is called the finesse. It's a function of the surface reflectivity. What have I done? Okay. Now, if I actually take the parameters that you see in the table on the other side and plot what is the reflection and the transmitted and reflected beam, you can see this type of transmission and reflection comb, and the resolution that you achieve from those parameters is 9 times 10 to the 5. So I actually have an order of magnitude increase in the resolution just by using this ettalon. However, you can also see a problem here, and the problem is that, okay, I got very, very narrow peaks, but my sampling is discontinuous. I don't really have a spectrum, I have sampling, and therefore I need to solve this problem. And the way that I thought of solving that is that, okay, the beam reflected is reflected with very, very high efficiency. So I would just add another ettalon at the reflected beam. The reflected beam intersects another ettalon, and this ettalon has a condition in which the lambda tag, the transmission peak, is actually shifted by a little bit. For example, in the case that I showed you, if I increase the thickness of the piece of glass by 33 nanometers, I will get the second transmission curve that you can see here. And this will be the reflected beam from those 2 ettalons combined. I still have a lot of things to sample. And I think that from here, to make the huge leap of putting A together to sample everything is kind of straightforward. Overall, a CAD illustration of my design can be shown here. We have a fiber input from the telescope. It goes into this 9-fold reflective polygon, which I'm very proud of. And then it goes into 1 echelon reflected back, 1 echelon reflected back, and so on 8 times. We still have a problem. And the problem that, okay, each echelon still has sampling. It doesn't have wavelengths. It has all the peaks of that specific echelon, and I need to separate them. However, in order to separate them, I don't need very high resolution because the spacing is so much higher. In fact, I can use G-clef at its medium resolution mode in order to separate them. Any instrument that have a free spectral range of the order of the free spectral range of the echelon will allow me to separate the orders. For example, G-clef at the GMT has a resolution of, when it works at the MR mode, has a resolution of 40,000. Ectoshell at the MMT, or we can think of designing whatever we want. Then each fiber goes along the slit of the spectrograph, and when I look at the CCD, then I'll get from each one of them a spectrum, and each spectrum will achieve a resolution of, in that case, 3 times 10 to the 5, 5 times 10 to the 5, whatever the parameters that I want. So overall, the diagram is I have a point source, goes into a collimator, Fabry-Perot instrument, long slit, a shell spectrograph, and spectral product. Now you can ask me, okay, you say that the problem was that you can't build a large enough shell spectrograph because the grating is very, very big. Did you actually solve the problem? Maybe the echelon needs to be 5 meters big, and then you have wasted our time. So it all governs by Etendu, which is the Lagrange conservation. So the Etendu of an FPI is given by this term, where S is the surface of each echelon, K is a factor of order 1, and R is the resolution. This is the Etendu of the telescope, and if I combine the two, I will get an equation for the minimum size of the Fabry-Perot. And a Fabry-Perot echelon with a resolution of 9 times 10 to the 5 on the MMT has a size of 7.5 millimeters. The same shell spectrograph, I will require a shell of 2.5 meters. Going to the GMT, I will need 30 millimeters. If I want to build the same thing with a shell spectrograph, that will be a 9.7 meters. Overall, this beautiful instrument can fit in Armando's pizza box. I tried to find a picture of his box online, but okay. So again, an illustration of the entire process, transmission spectroscopy, Fabry-Perot, shell spectrograph, and high enough resolution. And now you can ask me, okay, does it actually help you? So we actually simulated it. I created a Monte Carlo simulator of an FPI array with an external spectrograph. I took a spectrum, guys here gave me spectra of stars, exoplanet atmospheres, telluric, and I just created a pool of 1,000 observed transits of an M4 star with an Earth analog in the habitable zone. And doing a bootstrap analysis and determining what is the sigma of detection. And this is the money plot. So with an shell spectrograph at the GMT with 10 to the 5, I needed around 34 transits in order to actually detect oxygen in the atmosphere. However, with the FPI array instrument, I needed either around 26 or around 24 transits with the instrument that I showed. I'm almost done. However, this is not the only thing that you can improve. So far, when I showed you the transmission curve, you saw that the lines are very, very narrow, and actually that affects my efficiency very much because I lose most of the photons, or 50% of the photons. So in a visit to a vendor that's actually manufactured for me that, I saw something that is called a dualon, and I asked them what do they do that, who do they build it for, and they tell me that they can't tell me, so that means Air Force or whatever it is. And I thought, okay, can you show me some information? He showed whatever he could. And I thought, okay, a dualon is basically what happens when I take two echelons and stick them together. If I actually control the parameters of the reflection coatings well enough, I can actually create a transmission curve that is much broader, and actually also the out of band reduction of the throughput is much better as well. This is the blue curve that you saw here. So that actually has an efficiency of 2.2 times the efficiency of a single etalon. And that's kind of tells you why it's really worth sometimes going and paying a visit to vendors. Because I couldn't find in the literature anything about this dualon, but paying a visit, seeing something about it actually gave me an idea. I can actually improve that. In addition, we can build a dedicated external spectrograph with dedicated coating. One of the things that came to my mind is that, came to me and Mercedes' mind is that, okay, for example, when I observe in transition, part of the time I'm wasting on readout, and therefore maybe using frame transfer CCD, I won't lose on readout, I will be able to continuously monitor the transit, and so on. There are relevant, many other science cases I think that this is relevant to. I talked with Avi about that, and naturally came the Sunday lobe effect, a study of low metallicity stars, velocity dispersion measurement, and so on. And if you have an idea of something else, please let me know, because we plan to actually build it. I'm now building a prototype. I'm supposed to get the critical parts early April. I talked with them yesterday. This is where we are measuring that. This is my vacuum cell at the CDP. And my collaborators are Mercedes, Andy St. Georgi, Juliana, who's a grad student here, works with me as well. And we have Gonzalo Gonzalez Abad that gave us the transmission spectra, made the models. So in case you need any more details, please contact me. I think I lost the pattern the moment that I told them what I'm going to do with that, but no, I didn't. There are many reasons for that. There's also applications in other fields other than astronomy. It's true. I'm not a very good businessman, I have to be honest. That's why I'm here. But,
No, it's a beautiful idea. What is the throughput, though, with all these reflections?
so overall, when you are looking at a narrow band like the oxygen band, you can get a throughput of 95% from a dualon, for example. That's the actual throughput. The problem comes when you are looking at a broader band. But the way that I see these kinds of instruments, it's building a race car rather than an SUV. It knows how to do one thing, and it does this one thing very, very well. It won't take your children to soccer practice. So this is the way that I see it. You can think of creating different etalons, because the etalons are relatively cheap, relatively, yes? It's not like you can buy them in the supermarket. You can think about, okay, if I have, for example, something for the C1 line, then okay, I will buy a set of etalons just for that, and I will attach that when I do that observation.
How does the number of etalons scale with resolution that you want to achieve?
The number of the number of etalons scales by the free spectral range of each etalon and the resolution of the external spectrograph. So, for example, I could do just with 2 etalons if I use GCLEF at its higher resolution mode, but then the highest resolution mode, actually, I will lose more photons because I'm using a mode in the external spectrograph that is less efficient. So there's a balance there.
Given the structure of the TMT with the 7 mirror design, do you treat this as one combined mirror for this purpose, or do you treat the 7 mirrors as 7 parallel telescopes?
No, in this case, I don't need to pupil slice. What you're talking is about pupil slicing. In this case, the calculation that I presented here, assume that you are not pupil slicing. So you are actually saving this along the way. You can act as if this is a single telescope.
So my question is it more straightforward to treat it as 7 telescopes?
You don't
need to have ADWS working perfectly.
It's true, you could do that, but then you'll have a different problem of actually fitting everything through the fiber and making. But in general, it's true, and then the size of each etalon won't need to be 30 millimeter, but 7.5 millimeters. But unlike in a regular spectrograph, and okay, it goes from 2 meters to 15 centimeters and make it possible. Here, 30 millimeters or 7.5 millimeters. Both of them are possible.
Well, we got to our time limit. More questions. Thank you all for coming.
Thank you.
I have a question. You have the dual lines that have the broader
Transmission curve. Yeah.
Do you need a higher resolution in the spectrograph at the end?
No, because the issue is that if I look at the resolution of as my full width half max, as long as I can fit my full width half max in the same way, they won't necessarily be broader, but they will have a tendency to have a flat top. So they will look like that. They will look like a top hat function.
Right.
It's not like you definitely damage your efficiency. The downside with the dual-ons is that they are very, very hard to manufacture. You need a very fine fitting of the resolution between those two to a level of like a sub-nanometer level. Okay. So, you know, if an etalon costs $10,000, a dual-on costs $65,000.
So I think it sort of came up a little bit at the end that there was that you're talking about a very narrow wavelength.
It will function in general. Yeah. Oh, I almost.
Unless you want to take it around.
No, God, no.
Great, thank you so much.